All right, well, welcome everyone. I am JJ. Let's tackle an example problem. We're saying here we have a beam shown is supported by a pin at A, and then our cable that goes from the beam up to the wall at point B. Let's find our support reactions. What's going on at A? What's going on in the cable? So we'll start out and make a free body diagram. We know if we're doing that, we're drawing. If we circle around this, we'll slice through that cable. So it's going to need to show up in here. We're going to cut the pin, and then I can close out my circle. So everything in there needs to get included. That means my distributed loads, my force here. I cut my pin, so I'll put it in, and I cut the cable. So I'll show it as well. So let's come down below. Actually, let's do this one just to the right side here. It's a little bit smaller. So we can get that in here. We have our beam. We cut a pin here at the beginning of this, so I need to put in X and Y components on that. An AY and an AX in for this. I'm going to assume that goes up and to the right. AY and AX. We also can come in and say we cut through a cable in there. That cable at B. If I slice that cable, I should put it in. Well, I guess directions for AX and AY. A cable, I know a cable has to be in tension. This is the one support reaction I should be able to get correct every time. I'm going to show it. It should leave my circle. So it's going up and to the left. I'm going to have some tension in here. All that we know is it goes to point B. So let's just call that TB, the tension in cable B. I also know that from that cable to the right edge of our beam, that's just 1 meter. And the far right edge, there's a 4 kilonewton force coming straight down. 4 kilonewtons. I know there's two 2-meter distances here. I'm not going to worry that my 2-meter distances both look like they're smaller than that 1-meter distance. It's not really the most pertinent part of our problem, but get your distances labeled in here. I have in the first 2 meters a triangular distributed load. So I just replicate what was given in there. Redraw the triangle for this. And my maximum height of that was 3 kilonewtons per meter. So we'll label that 3 kilonewtons per meter. That's the tallest side of the triangle is what we're saying there. Finally, the last thing I need is what's this angle for TB? I should be able to figure that one out. That cable goes over 2 plus 2, 4 meters along the beam and up from A to B. It goes up 3 meters. I could figure out an angle for that, or I could recognize, well, that means I went over 4 and up 3. This is a 3, 4, 5 triangle. And I could just label that. But that gives me enough. I can find my unknowns for this. Right now in the X section, I have AX and TB. In the Y, AY and TB. Let's sum moments to start this out then. Ideally, we'll get rid of 2 of our unknowns. Really, I could sum moments here at A. I get rid of AX and AY. Another great place for us, I could sum moments here at whatever this point is. And I get rid of AY and TB, or sorry, AX and TB. I'd be able to find AY. Or realistically, this one's a little bit trickier to see. But if we look at our given picture, if I sum moments up here at point B, assuming it's directly in line with A, if I sum moments here, I get rid of TB, and AY passes through that. I can find AX out. There's 3 places I could go. I would just say, well, which one's going to be the easiest for us? The easiest is probably the one that I would find first. That'd just be summing moments at A. So sum moments at A. So it's positive, going counterclockwise. Summing up our moments about point A. I'm going to get that is, well, I'll have moment from the distributed load, from TB, from my 4 kilonewtons. Let's get TB in there first. It'll be counterclockwise for the Y component of this, so it'll be a positive moment. So I'll have force for the Y component. That'd be 3/5 of TB. Force times distance, 2 plus 2 is 4. And then we'll come in and do that same thing. Let's do the 4 kilonewton force first. It'll be, my force will cause a clockwise rotation, so I'll subtract this off. Force is 4. My distance is 2 plus 2 plus 1, 5 meters. And then finally, one last thing to deal with, I need that distributed load. That whole distributed load will cause a clockwise rotation, so minus Remember, the force part of a distributed load is the area. So the area of this triangle, the triangle's area is 1/2 base 2 times height 3. Where this is the area, which equals the force for our moment in here. I'm not done though. For moment, I need force times distance. The distance should be to the centroid. The centroid of a triangle is 1/3 of the way into the triangle. We have to measure that from the 90-degree corner in that triangle. So measuring from the right side of that triangle, I need to get 1/3 of the way in. But I'm measuring my moments from point A. So my distance term in here, I'm going to say, well, what's my distance from A to that 90-degree corner? It's 2 meters. And then I backtrack. I come back towards A 1/3 of the distance. So if I'm backtracking, I just subtract the distance off. 2 minus 1/3 of the base. Well, the base is 2, so minus 2/3 will be 1/3 of the base. And that's my distance term. This is D. Again, to 1/3 of the way in, measure from the 90-degree corner on that. The other way we could look at this, I try to just memorize one thing because I'm more likely to apply one thing correctly. But we could also say, rather than just memorizing 1/3 of the way in from the 90-degree corner, we could say, well, that's the same thing as 2/3 of the way in from the pointy side of a triangle. 1/3 would get us about here from the 90-degree corner. 2/3 would get us about the exact same point. Coming from the other side. We could have just done, well, 2/3 of 2 would be 4/3. 2 minus 2/3 is also 4/3. We're getting the same point. It's easier for me to memorize one thing and apply it, though, so I typically write it out that way. Well, this is everything for our moment, so we can set that equal to 0. TB is our only unknown in here. If I solve for TB, I'm going to get that the tension in cable B is 10 kilonewtons. And that's one of our answers. From here, I don't put the direction on this one because it's in tension. It's always along the cable. We shouldn't need it. But then let's go ahead. We can sum forces in either the x to get AX or the y to get AY. Either way, we're getting answers out. Let's go ahead and sum forces in the x direction. If I do that, I have my AX goes to the right. And the only other x force I have in here is from the cable. It's going to the left, so I subtract it off, minus the x component. Well, that would be the x leg of the triangle divided by the hypotenuse, 4/5 times our force. We just found TB was 10. That should get us to 0, which if I solve for AX, I'm going to get that AX is 8 kilonewtons, and it's going to the right. Finally, our last unknown is AY. I can sum forces in the y to get that one calculated out. Summing forces in the y direction. I have AY going up. I have TB goes up, so I want the y leg of my triangle divided by the hypotenuse. We're adding this in 3/5 of my tension in B, 10, minus 4 from my known force. And then I need to subtract off my distributed load. Again, if I'm looking for distributed load, if all I'm doing is forces, I just want the area of this. So minus my area, 1/2. My base is 2, my height is 3. 1/2, 2 times 3. Again, just because everyone struggles with this when we start out, this is the area of my distributed load, and it is telling me what's the force. Area equals force for a distributed load. So just find the area. But that's everything. We can set this equation equal to 0. I can come in and solve for my unknown AY. And I should end up that AY is just 1 kilonewton going up. AY is 1 kilonewton going straight up. Which would be my final answer. I'm just going to make my 1 a little bit more clear. 1 kilonewton going straight up. Again, we can tackle these. Distributed loads, we just need force times distance for moment, area times distance to the centroid, 1/3 of the way in from the 90-degree angle on a triangle. Or for summing forces, we just want to take the area for it. But hopefully this was a useful video for us. If it was, hit those like and subscribe buttons. Stick around, watch some more videos. Let's get you an A with JJ.